This is a video tutorial on properties of steam. In this tutorial, we are going to talk about the concepts related to the enthalpy of steam, the volume of steam, and such which are needed, particularly in solving some of the numerical problems. Now, these concepts would be applied in, I'm going to give you some certain examples which are coming. For example, one is to calculate the boiler efficiency. When you want to calculate the boiler efficiency and you want to find out the thermal output of the boiler, you need to find out the enthalpy of the steam. Now, the steam could be superheated steam or it could be wet steam. Then how to calculate the enthalpy of different conditions of steam? That is one thing we need to know. Then another types of problems are coming that when you are using the flush recovery vessel to recover some flush steam from the hot chimney. Now, how much of that flush steam recovery is possible? And that calculation would also require the concepts of steam problems. Then the calculate the pipe size to carry a particular amount of steam at a particular condition. For that, you need to know or you need to calculate the specific volume of the steam. And then there is also sometimes they may ask you the quantity of a temperation spray in order to control the steam temperature. So what we do is we take a look at the concepts. Let me tell you, these are very simple concepts as such. If we are thorough about the steam concept and then we practice with some examples, it will not be very difficult for you to get into it. Let us start with the basic understanding we had in the first tutorial, that when we calculate the heat, or we want to assess the heat in water and steam, there are two parts. One is the sensible heat and the other is the latent heat. Sensible heat we can calculate as mc delta T. The latent heat, for that we need to refer the steam channel. Okay. Now, some useful informations in this regard which we must remember. First of them is the enthalpy. Now, what is an enthalpy? Enthalpy is the total heat content. We know all of us. We know that enthalpy is the total heat content. Now, when we talk about enthalpy of water and steam, it is the total heat content, but when it is measured from 0 degrees centigrade, that means the measurement starts, the enthalpy measurement starts at 0 degrees centigrade water. Therefore, 0 degrees centigrade water enthalpy is 0. From there onwards, any amount of heat added will be considered as enthalpy, the total heat content of water as well as steam. The temperature at which the phase changes from water to steam, we know that usually we used to call it boiling point, but from now onwards that will be considered as a saturation temperature. And this saturation temperature again is not necessarily 100 degrees centigrade all the time. It changes with pressure. Higher the pressure, more will be the saturation temperature. Under atmospheric pressure, it is 100 degrees centigrade. And at saturation temperature, when the heat is added, it is added without any increase in the temperature at constant temperature. This part of the heat is called the latent heat. Right? Now, if I want to take a look at the graphical representation of the relationship between the enthalpy and temperature when water is heated, let us consider that when the water is heated under atmospheric pressure, and let us start from 0 degrees centigrade water. So at 0 degrees centigrade the enthalpy is 0. So when we add heat at this point, the enthalpy increases and we mark that on the x-axis, which is the enthalpy axis. Since it is the sensible heat, correspondingly mc delta T, the temperature is also going to increase. So we mark that in the y-axis, temperature axis. If I extend these 2 points, they are going to intersect at one point of time. Now this way I go on adding heat and I go on increasing the enthalpy, I go on marking it on the x-axis, and I know that under atmospheric pressure condition, this I can continue till the temperature reaches 100 degrees centigrade. So at this point, let us have 2 more points, and enthalpy axis and temperature axis. Now we extend these 2 points, we get another intersection. Now we have got 3 reference points, 1 starting and 2 mid intersection points. When we join this, we get a line. Now this line represents the relationship between temperature and enthalpy when water is heated under atmospheric pressure condition. So we call it an atmospheric pressure line on temperature enthalpy relationship. Okay, at this point, 100 degrees centigrade, we further add heat. We know that when we add heat, the total quantity of heat will increase, therefore enthalpy will increase. So we mark that on x-axis. But since it has reached 100 degrees centigrade atmospheric pressure condition, which is the saturation temperature, now the phase is going to change, but the temperature is going to not. Therefore, the line is going to take a parallel to the x-axis. Temperature will not increase, therefore the line will be going like this. And this thing is going to continue till all the water molecules will become steam molecules. Enthalpy will increase, temperature will not, and the line will stay parallel to x-axis. Now at this point of time, when let us assume all the molecules of water has become molecules of steam, if we add heat, again it will be sensible heat. The temperature along with the enthalpy both will increase. They will follow the relationship mc delta T. Relationship mc delta T here as well as here, only difference here the C was of water, here the C would be of steam. Now this line which I have got is the temperature versus enthalpy line of water and steam when water is heated from 0 degrees centigrade under atmospheric pressure condition. Now what happens if the pressure is more? We know that when the pressure is more, the saturation temperature will not remain 100. It will require more enthalpy, sensible enthalpy, and the temperature will further increase to reach the point when it will become saturated, right? So the line will not stop here and turn. It will continue till this point and then it is going to turn. So at this point, if I increase the enthalpy, similarly what happened in the lower line, the temperature will not increase, therefore the line will remain parallel to the x-axis till all the molecules of water become steam. Once it has become totally steam, then the enthalpy will increase as well as the temperature, right? And the line will again take an upward curve like this. Now, this way, I can continue having different pressure lines at higher pressure, higher pressure, higher pressure. For example, let us say A, B, C, D is one pressure line, okay? Then I have got a higher pressure line A, E, F, G. Then perhaps I put even higher pressure and the line will go to A, H, I, J. Similarly, even higher pressure A, K, L, M and such. Now one thing is to be noted here is that B, C, both are the same temperature, right? Now this point B and the point C, one thing is common is the temperature, but one thing is not common is that at point B, 100% is water molecule, at point C, 100% is steam molecule, right? Similarly, E, H, K, 100% water molecule, L, I, F, 100% steam molecule. Now these points we call the saturation point on water line, and these points we call the saturation points on steam line. If we join this saturation point on water line and steam line, what we get is what we call the temperature enthalpy diagram, right? It is a little different than the temperature entropy diagram which we are more familiar with, right? The look is like this instead of that typical hump of temperature entropy diagram. One thing, in fact several things can be noted from this diagram. One is that BC was the latent heat in this pressure line, which is EF on the higher pressure line, HI on the even higher pressure line. So as the pressure goes up, the latent heat part is going down, down, down and down. And this way if we reach here, which is a line corresponding to the absolute pressure of 220.9 bar and the saturation temperature will be 373.14, the latent heat will become 0. Now this point is called the critical point, the critical pressure and the corresponding critical saturation temperature. If your boiler is operating at a pressure more than this, then we call it a supercritical boiler. And any boiler working with a lesser pressure than this are called the subcritical boiler. Okay. Now, again, if I want to correlate this temperature enthalpy diagram on the boiler components, right? I would see that from here to here is the sensible heat part, right? From here to here is the latent heat part, and from here to here is the superheat part. Therefore, the sensible heat part is gained in a thermal power plant boiler in the, if I say this is the condensate extraction pump. So from there to the LP heater where the temperature is increasing, from there to the deaerator where the temperature is further increasing, from there to the HP heater, before that there is a feed pump, then the HP heater where the temperature is further increasing, then the economizer where the temperature is almost but not reaching to the saturation temperature, right? At this point perhaps it is entering the drum, right? But the moment it has come to the drum, the water becomes saturated water. So this is the point which I am going to find inside the drum, water, right? Now here in the evaporator, the water is continuously getting converted to steam, and that steam is getting separated by the separators and going to the superheater. But if I ask you that where would be the saturated steam here, that the saturated steam would not likely to be found here because the separators are not expected to work with 100% efficiency. Therefore, we might find some amount of water here. But I would say that at the inlet of the superheater here, right, here the steam will be totally saturated, dry, and then the temperature will rise to the superheater temperature, right? So this is how we correlate with the boiler components, the heat gained at various boilers, heat exchangers with the temperature enthalpy diagram. So the next thing is the enthalpy calculations, the specific enthalpy of water. That is the first thing. Usually the specific enthalpy of saturated water, if we consider when the water is at saturation temperature, then we need to find it out from the steam table, right? This part of the sensible heat is the enthalpy, sensible enthalpy of saturated water. We get it from the steam table. It is denoted by HF. Now, specific enthalpy of water at any temperature, if it is not saturation temperature, in that case, please remember, we cannot refer the steam table. If the temperature has not yet reached the saturation temperature, we have to use the sensible enthalpy relationship MC delta T, right? Therefore, if I say specific enthalpy M would be 1, right, and delta T would be from 0 degree to that T, so that is T minus 0 would be T, so MC delta T becomes CT practical, right? Now remember, this is a very common mistake sometimes done. Whenever you are given a feed water temperature and you are asked to find out the enthalpy of that water, you first see whether the temperature is saturation temperature or not. That means it has already reached the saturation condition or not. If not, then you cannot refer the steam table to find out, because usually what people, the common mistake is the people go for the lower temperature, saturation temperature, and they match the temperature with the steam table and they get the sensible enthalpy from there. It is not to be done. You have to understand that at your pressure, for example, if I say that at 10 bar pressure my water temperature is 150 degrees centigrade, what is the enthalpy of that water? Now I need to remember at 10 bar pressure the saturation temperature is 179.9, close to 180. Therefore 150 degrees centigrade water is not yet saturated water. Therefore I cannot just find the steam table, find where 150 degrees centigrade temperature table is given and corresponding enthalpy I cannot take. I have to go with CT. That is, I take the specific heat of water as 4.187 and T as 150 degree. So simply CT, right? It is very important. Do not make this mistake. Now, specific enthalpy of evaporation is the part of heat which is added from saturation temperature after it is reached, right? And the conversion is taking place from here to here, right? This part, and again it is found from the steam table and denoted by HFG. The enthalpy of dry saturated steam is nothing but the enthalpy of specific enthalpy of sensible enthalpy of saturated water and the enthalpy of evaporation. You add this two, you get the specific enthalpy of dry saturated steam. But again, this is denoted by Hg and it is also available in the steam table. You don't have to add HF and HFG from the steam table, right? And now let us see how a steam table should be seen, or how should we read the steam table. When you take out the steam table, there will be two types of steam table. One is the pressure based, another is the temperature based. Now the pressure based steam table, the first column, let us say this pressure line, the first column would be the absolute pressure. Okay, here please remember the pressure given in the steam table is absolute. Therefore, if the pressure in your numerical problems is not mentioning absolute, you might have to write that assuming the pressure as absolute. Please do not forget that. Make it by default application. Every question should start with assuming the pressure given as absolute, unless they have mentioned it or they have specifically mentioned it as a gauge pressure. So the first column would be the absolute pressure. Usually you are going to get a steam table in bar, not kPa. Here it is shown in kPa. The next column is the corresponding saturation temperature, Tsat. Okay. Then the next two columns are the volume columns, specific volume columns. Specific means volume per kg, right? The first column is this one. This is the specific volume of the saturated water, that is the water at saturation temperature. And the next column is this column, which is denoted by Vg, is a specific volume of the saturated steam, dry saturated steam, right? The next three columns would be for enthalpy. The first is the specific enthalpy of sensible enthalpy of saturated water, HF. The next part is the specific enthalpy of evaporation, that is the latent heat, HFG. And the third is the addition of these two is the specific enthalpy of dry saturated steam, that is H, right? Now, if it is a wet steam, what is wet steam for the matter? Wet steam is that the latent heat part, if it is not fully received by the water, let us say 1 kg of water has not yet received the total HFG, it has received only, let us say, X part of the HFG, then the whole 1 kg of water will not become 1 kg of steam. It requires the whole amount of HFG to become 1 kg of steam. So therefore, this steam will have some amount of water. So whenever there is a wet steam, you get another quality, or rather one more specification is to be added, that is the dryness fraction, right? The dryness fraction is the fraction of the dry steam in that steam. If let us say we have got 0.9 kg of steam and 0.1 kg still water, then the dryness fraction will be 0.9, right? It is basically the mass of dry steam over the total mass of steam. But another way, if I understand that, you see, the dryness fraction is nothing but the fraction of HFG that is being received by the water, right? So that is the concept, thermal concept of wet steam. That wet steam is, you can think this way, the wet steam has not yet received the total HFG. Still some HFG is left, okay? Whatever fraction of HFG it has received, that is the dryness fraction of that steam. Therefore, the wet steam enthalpy, if I want to find out, HF, yes, it has received totally. HFG, no, it has only received partly. So the enthalpy of wet steam will be HF plus X HFG. That is how you are going to find out the enthalpy of wet steam. So from the steam table, if I take a look how to find out the enthalpy of the wet steam, first you have to look at the pressure on the steam table. Now corresponding to that pressure, you find out the HF and HFG, right? You take it on the paper and then you use that HF plus XHFG enthalpy equation, right? Now, one common mistake you might not would like to do is that some people, they directly take Hg and whatever the dryness fraction is given, X into Hg, they calculate the enthalpy. Never do that, right? Because as I told you, waste stream has not yet received the total HFG. So whatever it is lacking is in HFG, not HF. HF it has received fully. That's why it has started becoming steam, right? So never take X into Hg. Always find out HF plus XHFG. Now, if it is a superheated steam, in a superheated steam, let us say is a superheated steam with a temperature T sub. The saturation temperature was T sat, right? So the amount of heat which has already received is the Hg, and this is the amount of heat which has been added to Hg. Now we know that this is a sensible heat, therefore it is going to follow MC delta T, right? Since it is specific enthalpy, M is 1, so it is C delta T, and delta T is T sub minus T sat, right? So the enthalpy will be Hg plus this sensible heat, that is Cp T sub minus T sat, and you can assume the Cp of superheated steam as 2.09 if it is not given, right? So you can either refer the superheated steam table if it is given to you, and in absence of superheated steam table, you can use the saturated steam table, from where you can get the Hg, the T sat and such value, and can still calculate the enthalpy of superheated steam, right? Okay. Now let us take a look at an example. Determine the quantity of heat required to produce 1 kg of steam at a pressure of 6 bar when they produced from water at 25 degrees centigrade. The condition of steam is given as wet, having a dryness fraction 0.9 dry. Okay, so they have given us what? So let us first put down the whatever the values they have given us. So they have given us the pressure as 6 bar, they have given us the temperature as 25 degrees centigrade, right, temperature of the water, and they have given us the condition of the steam as 0.9 dry steam. Now, if I see the 0.9 dry steam enthalpy, how much enthalpy is there? So for that I have to look at the 6 bar pressure in the steam table, and you have to take the corresponding HF and HFG from the steam table of the 6 bar, right? Then use the enthalpy equation of wet steam, HF plus XHFG. I get the enthalpy as 2546.99. Now, what is this enthalpy? Is the heat added to 0 degree centigrade water to get a steam of 0.9 dry wetness. I mean dryness fraction, right? So the heat which has been added, this amount of heat has been added to 0 degree centigrade water, but we have not done it with 0 degree centigrade water. Our water is at 25 degrees centigrade. Therefore, there is already some enthalpy, right? So 25 degrees centigrade enthalpy is, as I told you, Ct, right? So that comes to 104.67. This much amount of heat was already there. So additional heat which was required to be given was the difference of this, which is 242.32 kilojoule, right? So this is how this type of problems, this is a very simple problems. Similarly, you can find out the enthalpy of superheated steam and saturated steam. You can directly get it from the steam table. Now we take another example. For as I told you that sometimes this type of examples are also been asked. A CVD at a pressure of 15 bar is flashed to a lower pressure of 2 bar. If the CVD rate is 100,000 kg per hour, calculate the percentage of flash steam and the flow rate of flash steam. Okay. Now, first we take a temperature enthalpy diagram. In fact, I would suggest that whenever you have some problem with properties of steam, it's not a bad idea to draw the temperature enthalpy diagram and then have the concept on that. Okay. We have the temperature enthalpy diagram. Let us draw approximately. Let us draw the pressure line of 15 bar here and the lower pressure line of 2 bar here. Okay. Now CVD of 15 bar will be at this location, which is the saturated water. Okay. Now saturated water means the enthalpy of this water CVD is already, this part is there. Let us say it is HF1, and from the steam table at 15 bar we can find out the corresponding HF1, which is 844.6. When the water has been, it's throttled to this pressure, there is no loss of heat. That is the throttling process. There is no loss of heat in this process. So whatever the heat was there with this water is still here. But at this pressure, if it is water, then the maximum heat it can have is here, and that is the HF2 part. And from the steam table corresponding to 2 bar pressure, we can find out the HF2 is 504.7. That means the water, when it is coming to the flash vessel, to the lower pressure, it is already having some additional enthalpy. Now this part of the heat is going to convert the already saturated water to some amount of steam, right? Now if I had total of HFG at 2 bar, then 1 kg of water will become 1 kg of steam. But I am not having total HFG, right? So how much of that, let us say that is the HFG2, right? So the fraction of this heat over the HFG2 will be the amount that is going to get into steam. It will become steam, right? So quantity of flash steam will be HF1 minus HF2 by HFG2. Now this is a simple equation you have to follow. Only thing is mentioned that assuming no heat loss to the surrounding. So HFG2 at 2 bar we can find out from the steam table as this. Therefore, the percentage of flash steam can be calculated as 15.44%, and when we know the CVD rate as 1000 kg, the flow rate of the flash steam can be calculated as 154.4 kg per hour. Now, let us take a look at how the specific volumes are calculated. We have already seen the steam table that the specific volume of the dry saturated steam is given as Vg, that is in meter cube per kg, and the density is kg per meter cube. Therefore, we just inverse of the specific volume. 1 by Vg would be the density of the dry saturated steam. But if it is a wet steam, then what? Wet steam means, let us say x is a dryness fraction. That means x kg has become steam. Therefore, the volume of x kg will be x into Vg. But remaining 1 minus x kg is still not steam, it's still water. So the volume of 1 minus x kg would be Vf instead of Vg. Now if I comparatively see the value of 1 minus x into Vf, if you see the steam table for lower pressure, the value Vf is a very, very small value, right? And when I multiply with 1 minus x to that, the value will become even smaller. So we can very easily neglect this one, right? And we can say that the specific volume of wet steam is xVg only, right? And the density will be inverse of that, 1 divided by xVg. Now if I want to find out the specific volume of superheated steam, let us say at a temperature of T soup, we know that the volume of the dry saturated is Vg here. And let us assume the volume of superheated steam as V soup. Now, if you consider the superheated steam as a perfect gas, then it is going to follow the gas laws. And if I increase the temperature, the volume is going to increase proportionately. Like V1 by T1 is equal to V2 by T2. Therefore, V2 will be equal to V1 into T2 by T1. Right? In this case, T2 is T soup, T1 is T sat. Therefore, V soup will be Vg into T soup by T sat. One thing we'll have to remember, we are using the gas laws, therefore do not forget to convert the temperature in Kelvin. If you do not do that, you are going to get a wrong value of this. Okay, so this is how the specific volume is calculated. Let us take a look at an example using a specific volume. A process requires 60 pH of dry saturated steam at 7 bar. Determine the size of the pipeline. Take velocity of steam as 30 meter per second. So what we have? We have the steam flow, it is 6 ton per hour, and the pressure is given 7 bar. Now the steam flow 6 ton per hour, I can convert into kg per second by dividing by 3.6. So I get 1.67 kg per second is the mass flow of the steam. And the velocity is given as 30 meter per second. Now we know that there is a relationship between the the volumetric flow and the area and the velocity, right? And the relationship is like the volumetric flow is velocity into area, right? If I take the volumetric flow in meter cube per second and the velocity in meter per second and the area in meter square, I will get the unit matched. Therefore, I need to find out the Q, the volumetric flow in meter cube per second. I have the Q in the mass Q as kg per second. Therefore, I need to find out the specific volume in meter cube per kg, right? So what I do, assuming that again by default this pressure has to be assumed as absolute pressure. Assuming the pressure is absolute, I refer the steam table. From 7 bar pressure, I take the dry saturated steam volume Vg as 0.27268, right? You may also assume that you don't need to assume, it's already given, dry saturated steam. So the volumetric flow Q will become mass flow into Vg, that is 0.455 meter per second. So now using the same, area is equal to Q by V, area as pi d square by 4. I can find out the d, the size of the pipe as 0.139 meter. I can also, give you a nearest size of, this comes to 6-inch size. So I can say as a 6-inch pipe would be required. So that will be all for this tutorial. I don't want to, lengthen this one single tutorial. Next tutorial, I'm going to discuss about some more examples, finding out some more enthalpies and specific volumes. And again, I'm going to discuss about the how to calculate the internal energy of the steam, then how to calculate the different conditions when it changes at constant volume process or throttling processes, right? Meanwhile, it is not going to be a bad idea to practice with the examples which is given in chapter 2 in your study material. And if you have any questions, any doubts, you can always use the virtual classroom to come back to me, right? Thank you very much. See you in the next tutorial.